Okay,
Awesome.
for the last contribution of this session, so we have Matthew Ho, who's going to talk about scientific discovery from ordered information decomposition.
Yes, thank you very much, Guillaume. My name is Matt Ho, and I'm going to be talking to you about a new way to get information from your data and your networks. But I also want to point out, I'm very aware that it is 6 p.m. on a Friday. I am tired, you are tired, and I appreciate you for being here. That being said, I've tried to make the talk as fun and eye-catching. Oops, sorry. Yeah, very fun and eye-catching. Oh no. How do I go back? I'm spoiling it.
That's fun.
This is forward.
Yeah, this is forward.
Damn. Well.
We're awake.
Yeah. What I was gonna say is I just have 2 slides of theory I need to get through, and then I have all the fun stuff, okay? Which you already know. So let's get through the theory, and then we can get to the fun stuff, okay? I'm just not gonna use it.
Yeah.
Okay, so at this point in the conference, I don't need to tell everyone what an autoencoder is. But just in case you don't know, the reminder is that what we're trying to do with a neural network autoencoder is input some data and output something that looks just like our data. And usually it's trained with this like mean squared error loss function, where all you're trying to do is get the output of the neural network to look just like the input. But the problem is, with an autoencoder, you often have a bottleneck, which is smaller in width in dimensionality than your input. So you need to figure out how to embed information into that bottleneck in order to get the maximum possible reconstruction. And these are really useful for a whole bunch of things that we've already discussed in this conference about compression, regularization, anomaly detection, generation, etc. Right? But if you've ever worked with an autoencoder, you know that the performance of an autoencoder is highly sensitive to the design choices of your network, specifically this bottleneck. And theoretical and empirical evidence has shown that the intuition for choosing the bottleneck size is not clear. Even in some cases, reducing the size of the bottleneck improves your reconstruction at the end. Okay? So how can you address this? Well, one thing is you could try every possible bottleneck and train a neural network for every different configuration. Or you can do them all at the same time. So this is my proposal. Bear with me for a second. I introduce this new bottleneck operator called an Information Ordered Bottleneck. And what it does is it looks at a given latent layer in your neural network, and it has the option, according to what k threshold you set, to zero out different parts of that latent vector. Okay? And literally, the practice of doing that is you take whatever inputs were originally to that latent vector, and you multiply them by 0. Okay? But the structure with which it does it is very special. It does it in this way that's shown at the bottom, where the red points are the ones that are blocked, and the white points are the ones that are open. Right? And it opens these latent nodes in this hierarchical way, such that if one node is open, then all of the nodes above it are also open. Right? So functionally, what this becomes is an autoencoder with a variable length bottleneck, which is specified by this value k. Right? And my proposal is that you train this bottleneck with the loss shown at the right, which is that each batch you pass through your neural network, you try every single configuration of bottleneck and prevent some of the information from going through. Okay? So let's assume we can optimize that loss function. What does that mean exactly? Right? That means that the neural network has to figure out how to force as much information as possible through the only bottleneck nodes that are open, specifically the ones at the top, right? So it's going to try to get the most information through the most reliable bottleneck, which is the one at the top, and then the second most information from the second, the third, and so on, okay? So in this way, you then have an information ranking within the latent layer of your neural network, such that at inference time, you can then change this slider and see how the reconstruction changes as you allow more information through. Now, does anyone recognize this loss function? It's exactly equal to PCA if your loss function is a mean squared error and your neural network is entirely linear. Right? So effectively, what we've done is created nonlinear PCA with the neural network. Now, that's the theory. The whole rest of the talk is me trying to convince you that this is a useful application for the variety of amazing things that you guys are doing. Specifically, here's a bunch of applications that we've investigated, and I'm going to show evidence of these things, including explainability, intrinsic dimensionality estimation, manifold fitting, symbolic regression, and complexity ranking. Okay, this was supposed to be the reward. This is my dog, Andre. He lives in the US with my partner, and ever since moving to Paris, I miss him very much. And looking at photos of him makes me happy. So what I want to do is ask generative AI to give me more photos of my dog. And if you've ever played with these things, the way it works is you give a prompt to an embedder, an encoder, right? Which is usually a transformer, and it can take either image or text. It then embeds that prompt into a length 768-dimensional vector, and then passes that vector, that sequence of numbers, to a diffusion model, which then creates an image, right? So every piece of information about my dog Andre is stored in that 768-dimensional vector. And it can create an image that looks like this, which is remarkably similar to my dog. It has the right colors, it even has his pink little ears, and it even has the background right. You can see it's taken on a hill with buildings in the background and a sunset, right? Remarkable. So why do I need a dog if I just have these 768-dimensional numbers, right? So what I want to know is, what does my model think is important, right? Or what is there truth in latent space? Where's the information coming from? So what I'm going to show you is we've trained a IOB autoencoder to threshold the amount of information that gets to the diffusion model at the end. And what I want to show you is, as I open this bottleneck, how the diffusion model learns to create more information that's relevant to the prompt. Okay? So first, when the bottleneck is totally closed, you get nothing, a random image, mean field reconstruction. Even when I open the first few nodes, still nothing, right? What are these? These are just random images, right? And then all of a sudden, 3 nodes in, you get a whole bunch of grass, right? And then at 5 nodes, you get a bunch of grass and a weird fuzzy thing in the middle, right? But just 5 nodes, you get all the information relative to the 2 big things in the image, the grass and the fuzzy thing. Okay, and then at 10, we finally get a dog in the center of the picture, so only 10 numbers necessary to specify this. And then we start getting real physical attributes, right? We get the perspective of the dog. We get the coloring, the relative coloring of the body, right? And as we move forward, we start to get the orientation of the final image, right? And we start to open, give it more information. Now we're at 40. It gets really physical. This looks like a real dog, but not like my dog. Then we start to get the real colors of the dog, right? Then we get the background. So now you're on a hill. You're sitting on a hill, just like my dog is. You get detail. So now that dog is wearing a harness, just like my dog is, right? And now you get lighting. We're at 150 nodes, and you get the correct lighting that you're expecting, right? And you start to get details in the background. You get the buildings and such, and so on and so on. And then eventually you get to my dog, okay? So that was a qualitative example of how you can decompose the information in a pre-trained network. Okay, that's not the only application that we have. Now let's consider a synthetic example. I've taken a bunch of 32 by 32 image and put little circles, yellow circles in them. They're all shown on the right? And the yellow circles can change their position and their size. So 3 parameters, x, y, and radius, right? And I've compressed this data set using a convolutional autoencoder, and I've slapped in my IOB autoencoder into the middle. And I want to see how the reconstruction changes as I allow more information through, okay? And I've compared it to a baseline of PCA, which, as you can see, does absolutely terribly, right? But what you can see is, by around 3 nodes open, I get the first ball, usually the biggest one. And then around 6 nodes open, I get both of them. And then the reconstruction doesn't really improve after that, right? Is that notable to you? Because that's exactly the intrinsic dimensionality of the simulator that I used to create those images, right? Stated a little bit more quantitatively, I'm showing now on the y-axis the error in these predictions, and on the x-axis the number of open bottlenecks. So as you expect, the more bottlenecks you have open, the better you do, right? But what we can see in our linear IOB is that it saturates just about 7, a little bit close, right? And I've compared it to PCA and kernel PCA, which do terribly, right? So in the paper, which I've shown at the top right, we provide theoretical guarantees to identify that this is the true intrinsic dimensionality of your data point. So you can take any data set, compress it this way, and figure out how many parameters were used to define it. And in the paper, which I'm not going to expand now, we've tested this over a variety of different data sets, including like with 1 disk, 2 disk, 3 disk, 4 disk. And I've shown our predictions in stars and a bunch of other leading state-of-the-art things in the other colors. And the dotted line is the true. And we're almost bang on in like 3 out of the 4 situations, which is remarkable. Okay, that's all simulated. Let's get to real data. So this is work done by Amanda Liu, who's a graduate student at Columbia. And it's in response to the paper of Cosmology with One Galaxy, which you guys have already heard, in which you take a bunch of galaxy parameters and you try to infer the cosmology of the simulation that it came from, right? So we don't understand why that works, right? But one hypothesis is that galaxy properties live on a manifold in a high-dimensional space, which is defined by cosmology. And that figuring out which manifold the galaxy that you're looking at lives on, then you can figure out what the cosmology is. So Amanda has taken this IOB method and compressed 16 galaxy properties from the CAML simulations and studied how the compression varies as you give it different parameters. And what she has found is that, really, galaxy properties only live on a 5-dimensional manifold in a 16-dimensional space. So you only need 5 numbers to specify all the things about your simulated galaxy, right? And now the question as to whether or not that answers Paco's question at the top is not defined yet, but that's why this is preliminary work. Secondly, so it's a combination of all of them, right? So it's projecting all of them into this nonlinear space. Okay, almost done. Another thing that's very useful is some work by Xiaosheng Zhao, who's sitting in the audience right here, is trying to do symbolic regression in high dimensions. Clearly, it's quite difficult to do symbolic regression as the number of features you have to include stack up. So what I'm just showing is trying to use symbolic regression to explain the most important latent variable in building an emulator for the CMB power spectrum. And this is still very preliminary work, so take this with a grain of salt. But from our initial evidence, it shows that NS and tau don't appear to be the most important thing defining the CMB power spectrum. Okay. Lastly, I just want to mention this crazy system. This is GRS 1915-105. Right? It's a black hole binary system, and these are 5 light curves from the same system. Ridiculous. Tons of variability, right? And this is often referred to as the graveyard of theses, because many people have tried to describe it, and no one has a good physical model, right? So what we've done, and I know I'm almost done, is trained an IOB network to compress and study how many parameters actually dictate the different light curves that we're seeing, to explain all the possible modes of variability of this black hole binary system. And we're showing here on the right, the top is a light curve, and the bottom is the local intrinsic dimensionality of each part of the light curve. And we're working on quantifying exactly what each of these different dimensionality estimates mean in terms of theory and simulation. So we're really doing latent space exploration on real data, which I'm incredibly excited about. Okay. That's it. That's my conclusion. The paper is on arXiv, and all of the non-science examples are available on GitHub in that repository. You can try it out, or you can email me. Thank you very much.
Thank you. Any question in Paris? Well, there's one here. Just second rank. Yeah, your name?
Hello, I'm Ethan. That was a very interesting talk. I was just wondering, is it useful to have all the bottleneck closed? Would that be useful for like learning like a general average of it all?
Then you get the mean. You get the mean of your data. And if you notice, in this plot, I'm showing the variance, the mean squared error divided by the variance, right? And when all of the nodes are closed, you get the variance of the data set, which makes sense.
Thank you.
No problem.
Maybe one question in New York, and then if there is.
We have 2 questions in New York.
Okay.
Peter. Oh, that was your question. Okay. Yes. There, Karthik.
Hi, Matt. This is really fantastic work, and I am playing around with this already. My questions are, 1, can you comment about the orthogonality of the sort of latent dimensions that you find? And 2, is there any easy way to relate them back to the input features?
That's an excellent question. So on purpose, we're not imposing orthogonality of latent features. It's called disentanglement, and actually that's the subject of Luisa's work, who I don't know where she is. Yeah. So the reason we did it on purpose is because learning things like the X and Y position of balls in an image is really hard to do one node at a time, right? As I had mentioned in the debate on Tuesday, sometimes it's useful to take advantage of correlated information between latents. It just makes the learning of the neural network easier. Now that's not a hard and fast rule, but that was just from our experiments that you didn't actually need the orthogonality constraint. You just let the neural network figure out where it wanted to allocate its resources in and of itself. And relating it back to the inputs, maybe we can talk about that later on Slack for more details. Yeah.
Well, there was one question in the back, maybe here in Paris.
Hi, thanks for the very interesting talk, and it's super interesting work. I was wondering if the number of dimensionalities that you find using your method, like, would that depend on your architecture complexity? Because I was wondering, like, generally when you're using just normal autoencoders, there's always a worry that if you have a sufficiently complex architecture, would like end up in a lookup table effect. So could you comment on that?
That's an excellent question. So yes, as was pointed out, I think previously in this conference, any data can be put on the real line, right? So every compression would be just a straight line down and then to 0 if you had a perfect architecture and a perfect data set. However, it's really hard to get there. And so yes, our predictions are entirely contingent on the architecture we use. We've shown that it's robust to that choice of architecture in various cases, especially the cases that we showed. However, it is contingent. So even if you don't trust the intrinsic dimensionality estimates, it's still something to say about the relative complexity of different things. Because by assuming a fixed architecture, you're assuming a fixed smoothness to your data set. And things that can be fit with different dimensions of the same smoothness are differences of complexity. So that's still useful information, even if you don't trust the intrinsic dimensionality estimates.
I see, cool, thank you.
Okay, so let's thank all the speakers of this session again.